Okay, so it's 11. So if you guys want to get rolling.
Yep, okay. People are still joining, but let's get started. Okay, meeting is being recorded now. So welcome everybody to the 11th iteration of our ECS and Cloud Feedback Virtual Symposium. I'm going to lay out the ground rules again for people that might be new. So we usually have 3 talks. We only have 2 talks today. Matt Huber unfortunately can't join us anymore. So it's going to be 2 AGU style talks with questions after each of them. And I guess today we can have a longer general Q&A after the last talk. If you have questions or comments, type them into the chat at any time. We can read them out for the speakers and then they'll be on the recording as well. If you prefer to ask questions live, use the raise hand function from the reactions tab and we'll unmute you and you can ask your questions. If you have any questions or if you want to volunteer to give a talk in the future, contact our executive committee composed of the people listed here. All the videos of past talks, the link for the mailing list sign up, committee contacts, and more are available on our website. And with that, Jonah is going to introduce our first speaker.
Thank you, Christy. Thank you, everyone, for coming. Our first speaker today is Nicole Feldl. Nicole is an assistant professor at the Earth and Planetary Science Department at the University of California, Santa Cruz. And she'll be talking today about high latitude feedbacks. So Nicole, the floor is yours.
All right, so it looks like I need to steal the screen sharing away. So hopefully, okay. Great. All right, can everyone see my slides all right?
Yes.
All right, let me go ahead and grab this chat window too. Perfect. All right, well, good morning, everyone, or whatever time it happens to be where you're at. Today, I'll be talking about high latitude feedbacks with an emphasis on the lapse rate feedback, which has been implicated as a dominant contributor to Arctic amplification. And the lapse rate feedback is really interesting because it's not independent of other feedbacks, nor of atmospheric energy transport. And in this talk, I'll show a new decomposition that seeks to clarify the source of the lapse rate feedback and also reveals its state dependency. So global feedbacks and global sensitivity can be reformulated to assess the relative contribution of individual feedback processes to local warming. If we consider here the local energy balance for a column of the climate system, the balance is given by the sum of the local forcing, the local radiative response to surface warming, where lambda is the feedback parameter, and the convergence of heat flux in the atmosphere and ocean. From there, we can solve for the spatial warming contributions at equilibrium, where I've now separated out the atmospheric heat transport and the ocean heat uptake. And then all of these terms are normalized by the global mean Planck feedback to get units of temperature. On the right, I have an example of the zonal mean warming contributions in an aquaplanet model, averaging over the 2 boxed regions here and plotting those warming contributions against one another provides one attribution of Arctic amplification, which is shown in this plot here. So on the left, the farther to the top left of feedback or a process plots, the greater its contribution to Arctic amplification. And you can see the lapse rate feedback dominates Arctic amplification when plotted this way, not only because it warms the Arctic, which it does by about the same amount as the surface albedo feedback, but also because it cools the tropics. The same is also true of atmospheric energy transport, although that makes only a minor contribution in this framework. Whereas something like the water vapor feedback over here is positive everywhere, but it's much more positive in the tropics, and so it contributes to tropical amplification. Now, as seen on the right plot, the lapse rate feedback preferentially warms the Arctic in the winter. And the surface albedo feedback preferentially warms the Arctic in the summer, and that makes a lot of sense because it hinges on the presence of solar radiation. So let me take a moment to describe the lapse rate feedback and how it manifests differently in the tropics and in the polar regions. So the lapse rate feedback is defined as the radiative feedback associated with atmospheric warming that's vertically non-uniform. It's negative, indicated schematically on the left, where moist convection leads to greater warming in the upper than in the lower troposphere, which then strongly increases outgoing long-wave radiation. It's positive, which is indicated on the right, where stable stratification in the atmosphere, as you might see in polar regions, inhibits vertical mixing and traps warming near the surface. And so outgoing long-wave radiation still increases. It just increases less than it would in the case of a uniform warming. And so this warming profile is also characterized by a decrease in inversion strength or even a wholesale loss of the inversion. And mathematically, the lapse rate feedback is a residual that encapsulates, all the warming that's not vertically uniform. And our goal is to understand the underlying physical processes. So in the tropics, that seems to be pretty straightforward. Temperature profile is moist adiabatic, governed by radiative convective equilibrium. But in the Arctic, we have to consider a number of local and remote influences, which leads to some ambiguity as to what the lapse rate feedback means in the high latitudes. So let's consider sea ice. Here I'm reducing the ice albedo in increments in order to disable the surface albedo feedback, while still allowing the position of the ice to evolve according to surface temperature. So when the surface albedo feedback is positive, the polar lapse rate feedback is also positive. That's in kind of the mustardy color, and we have really strong polar amplification. However, when the surface albedo feedback is 0, when it's been disabled, the lapse rate feedback changes sign. It's negative now in polar regions, and there's no polar amplification. So in this mechanism denial experiment, you can see the coupling between these high latitude feedbacks. We can look at a very similar experiment now in a fully coupled model. So we have a greenhouse gas forcing experiment and an albedo reduction experiment. Using these two forced simulations, we can perform a pattern scaling decomposition of the temperature response, where we invert for the patterns that scale with low latitude warming and the pattern that scales with sea ice loss. So the part of the temperature response driven by low latitude warming in the bottom left includes polar warming of the mid and upper troposphere, whereas the part driven by sea ice loss is really localized to the Arctic lower troposphere. Now, by construction, the sum of panels C and D must equal the total force response in panel A. And for each of these temperature response patterns, we can then calculate a lapse rate feedback. And so that's what I've done here. So as you can see in the top panel of this figure, the Arctic lapse rate feedback is more positive under the sea ice albedo forcing than under the greenhouse gas forcing. Low latitude warming drives a modest negative feedback over the oceans and a modest positive feedback over the high latitude continents. But it's specifically the atmospheric warming associated with sea ice loss that produces this positive lapse rate feedback over the Arctic Ocean. And so that brings me to the new decomposition of the high latitude lapse rate feedback. So the goal is to isolate contributions to the lapse rate feedback from dynamically distinct atmospheric regions. So in other words, to separate the local surface-based mechanisms such as sea ice retreat from remote mechanisms such as atmospheric energy transport. Now, as shown in this figure, the 285 Kelvin isentrope is used as the basis for the diagnosis of the upper and lower lapse rate feedbacks. And because this isentrope intersects the Earth's surface in the mid-latitudes, it effectively isolates the high latitude, lower troposphere from both higher altitudes and lower latitudes. And then the lapse rate feedback is calculated using radiative kernels in each of these regions, and also for each model in the CMIT-5 abrupt 4 times CO2 ensemble. The upper lapse rate feedback, which is on the left, is broadly negative. It's greatest in the tropics where warming is greatest aloft. The lower lapse rate feedback then is positive in the Arctic, where there's snow and ice melt associated with the positive surface albedo feedback. And you can see it tends to be strongly negative over the Southern Ocean, where large-scale ocean upwelling reduces the surface warming and decouples the surface from the tropospheric response. And it's zero by construction in the low latitudes. The bottom panel shows PDFs of the feedbacks for the composite of all models and all grid cells for each polar region separately. And the result I'd like to highlight is in the two plots on the lower right, which show the lower lapse rate feedback plotted against the surface albedo feedback. And so you can see this positive correlation. A more positive lower lapse rate feedback is associated with a larger surface albedo feedback in both the Antarctic and the Arctic. And that makes sense because by permitting the surface to be colder than the overlying air, the presence of sea ice preconditions a large amount of surface-based warming when the sea ice retreats and the temperature inversion is eliminated. So we see a strongly positive lapse rate feedback over sea ice regions. That relationship is particularly striking in the Arctic, where the transition from a positive to a negative lapse rate feedback follows that 10% sea ice concentration contour really closely. In the Antarctic, the lower lapse rate feedback also tends to track the 10% sea ice concentration contour in individual models. But because of the large intermodal variability, the correspondence in the ensemble mean is much weaker. So that was for the annual mean, but we still need to understand how sea ice retreat, which is greatest in summer, affects boundary layer warming during winter, which is when the lapse rate feedback is most positive. So here I'm plotting local intermodal correlations among the CNET5 ensemble. The figure on the left shows that models with a larger reduction in summertime sea ice exhibit a more positive lower lapse rate feedback in late fall and early winter. That negative correlation is spatially robust across the region. A more detailed breakdown is shown in the subpanels on the right. So here we have larger decreases in summer sea ice concentration promote larger increases in surface turbulent heat fluxes in late fall and early winter. So that's consistent with an enhancement of the seasonal transfer of energy by ocean heat storage, as there is increased absorbed solar radiation in the summer that's then released back to the atmosphere in the winter. Then for larger increases in surface turbulent heat flux, the temperature inversion weakens more. You can see on the panel on the right in red, the dominant contribution to warming the boundary layer is indeed the vertical diffusion of upward surface sensible heat flux anomalies. And then for larger decreases in inversion strength, the lower lapse rate feedback is more positive, leading to further warming. So what about the upper lapse rate feedback and the remote influence of atmospheric energy transport? This figure shows the change in energy transport with models color-coded by the magnitude of the high latitude upper lapse rate feedback. So we find a larger increase in forward energy transport for a more negative upper lapse rate feedback, whereas for little to no increase in transport, the upper lapse rate feedback is less negative. And this relationship is consistent with that explanation that transport by preferentially warming the high latitudes aloft reduces the lapse rate feedback. And the partitioning of the energy transport reveals that increase in transport is dominated by the transient eddy energy transport, and it's particularly its latent heat component, which is shown on the right. And so that same correlation noted previously, where models with larger increases in transport are associated with a more negative upper lapse rate feedback, holds all the way across the circulation decomposition. It even holds for decreases in dry static energy transport by transient eddies. So a smaller decrease in dry transport also supports a larger increase in total transport because there's less cancellation, and hence a more negative upper lapse rate feedback. So all of these shade from red to yellow all have a negative correlation. And the largest reductions of the lapse rate feedback then occur for strong increases in latent heat transport by transient eddies that are only partially compensated by weak decreases in dry static energy transport. And so to summarize, the positive polar lapse rate feedback is fundamentally tied to sea ice. It's enabled by the presence of sea ice and enhanced by sea ice retreat. In coupled models, summer sea ice retreat leads to an erosion of the winter inversion via ocean-atmosphere interactions, which then warms the lower troposphere, promotes positive lapse rate feedback. And it's reduced in subpolar regions by increases in atmospheric energy transport, with the largest reductions occurring for the case of strong increases in latent heat transport by transient eddies. Now, I'd like to take one last minute to think about how we can leverage this lapse rate feedback decomposition to estimate the combined contribution of ice processes to Arctic amplification. So to do that, let's return to this plot style that I showed at the top of the talk, which again shows Arctic warming versus tropical warming for the various feedbacks, as well as atmospheric heat transport and ocean heat uptake. The X's are the conventional decomposition, and the O's indicate the present study with the lower lapse rate feedback combined with the surface albedo feedback, and the upper lapse rate feedback combined with the water vapor feedback. You can see in green that the combined water vapor and lapse rate feedback formerly contributed to Arctic amplification. However, under the new decomposition, it contributes neither to Arctic nor tropical amplification, falling right around the 1-to-1 line. On the other hand, the combined surface albedo and lower lapse rate feedback matters even more than under the conventional decomposition, shifting up along the y-axis and really dominating Arctic amplification as a coupled mechanism. So together, these two feedbacks are reflecting a season-spanning pathway by which the high latitudes are uniquely sensitive to a changing climate. And as a final point, an implication of this result for past or future warm climates is that the only contributions to Arctic amplification that would remain would be from the Planck feedback and atmospheric heat transport if you lose both the surface albedo feedback and the positive lapse rate feedback in an ice-free state. So thank you very much for your attention, and I'd be happy to answer any questions.
Thank you, Nicole. That was an excellent talk. Are there any questions from the audience? You can feel free to put them in the chat, or you can raise your hand. Was that somebody? If not, I guess I have a question. I imagine that, so the ice albedo feedback, no, I see Nader there. I'll get to you in a second, Nader. I imagine that the ice albedo feedback is quite state dependent. I was wondering if, what kind of ramifications you think this work has for considering examples from paleoclimate, like if you think that this lapse rate feedback would be present more in during the LGM or less during past warm climates?
Yeah, I think less in past warm climates because it would tend to be, what I think you would tend to get is just the negative, it would tend to be a negative lapse rate feedback everywhere if you don't have icy polar regions. And so, you know, I'm not saying you could still have amplification from atmospheric heat transport, from the Planck feedback, and maybe those would shift and adjust and look a little bit different than what I'm showing here. But I do think that the positive lapse rate feedback in the high latitudes and the surface albedo feedback are going closely hand in hand for an icy regime. Yeah.
Fair enough. Okay. I think Nader raised his hand. Do you want to ask your question, Nader?
Sure. Hi, Nicole. Thanks for the talk. Wondering about the importance of the upper lapse rate feedback and the atmospheric energy transport in general, I guess, in light of some of the older results of, say, Huang and Frierson showing an anti-correlation between atmospheric heat transport and polar amplification, say in like the earlier generations of models.
That's an interesting question. I guess there are two. I'm not sure like if there's a specific if there's a more specific question in there. I guess one thing that I could emphasize is that what I'm really focusing on right here is how changes in transport are affecting the lapse rate feedback. And so they'd be reducing the lapse rate feedback, but just to clarify, I'm not saying that atmospheric heat transport can't still directly cause Arctic amplification. If you have an increase in atmospheric heat transport convergence in the Arctic, that will warm the Arctic. You can see that in this plot right here. So there's still that kind of direct relationship. And what I've been focusing on in this talk is then an indirect relationship, maybe of how that affects the lapse rate feedback. So I think there are kind of two different things going on there.
Okay, that's helpful. Thanks.
Okay, yeah.
We have a question from Kyle. Kyle asks, can you say something about why the Planck feedback changes with the new decomposition, how to think about this change?
Okay, great question. So yes, so the Planck feedback also changes. The short answer is that under the new decomposition, the meridional gradient and the Planck feedback increases. So if that increases, then it's going to contribute more to Arctic amplification, which is shown here. So then why does it increase? Well, the Planck feedback is the uniform warming in each region where the lapse rate feedback is calculated. Since in the tropics, that's the same as it was under the previous decomposition, the Planck feedback hasn't changed in the tropics, but I have changed it in the high latitudes because you have a larger warming in kind of that lower tropospheric high latitude region, and it's smaller aloft. So that means that in the high latitudes, the Planck feedback is smaller. So if it's the same in the tropics and it's smaller in the high latitudes, then you have increased the meridional gradient in the Planck feedback, which then increases its contribution to Arctic amplification. So it's a consequence of kind of how I've changed this decomposition here, but the sum of the Planck and lapse rate feedbacks will still equal the conventional temperature feedback. So it just kind of shifted some of the warming patterns around.
Hopefully that answers Kyle's question. We have another hand up from Will Ingram. Will, would you like to ask your question? Maybe, oh, Will, are you there? Okay, well, maybe we'll move on to Steve Klein's question. So I guess this gets back to that that definition that you were describing. I don't know if you can see this question, but the concern is the definition of the feedbacks it's not actually an independent definition for the upper and lower lapse rate feedbacks, since the lapse rate feedback is defined as departure from a vertically uniform warming, then you cannot calculate the upper lapse rate feedback without knowing the temperature at both upper and lower levels. Hence, these components cannot be really separated. Although I think maybe you're saying that it's calculated in a slightly different way than that. But
yeah. So let me elaborate on. Let me try to answer this question. And I went back to this slide to maybe this will help explain what I did. So the big change here, so normally you would calculate the lapse rate feedback as the deviation from the surface temperature, from the surface warming, sorry. And so yes, you're right, the way I've separated it, I can't just use that same reference warming everywhere, or it would just be the same old lapse rate feedback. So here's the change up here in this equation. The reference warming for the upper lapse rate feedback is the temperature along this isentropic surface here. So I am indeed using a different reference warming. That's a deliberate choice because we want the upper lapse rate feedback. If the warming is uniform above this isentrope, then the upper lapse rate feedback needs to be 0. And so that was, a deliberate choice. So this would physically make sense. But it does mean that I'm using different temperatures for each, which also means that, getting back to Kyle's question, that there is a different Planck feedback in the high latitudes, which then increases the contribution of that term to Arctic amplification. In terms of them being, can these really be separated? I mean, I think that, the conventional approach is itself a pretty arbitrary way of decomposing the temperature feedback. So I think it's sensible in the low latitudes where the surface is coupled to the upper troposphere through moist processes. But in the high latitudes, constructing a lapse rate feedback around warming aloft relative to surface warming isn't really well justified. So maybe, are these entirely independent? Maybe not, but more so than before. And I guess I didn't emphasize this result, but you can see over here that in the Arctic, there's not a strong relationship between the lower lapse rate feedback and the upper lapse rate feedback. So you get this really strong relationship between the lower lapse rate feedback and the surface albedo feedback, but the decomposition does seem to be, the lower and upper lapse rate feedback seem to be pretty independent in the Arctic. And that's this plot right here that I completely blew past.
Thank you. Are there any more, if there's not any more questions for Nicole, maybe we should thank her and move on to the next speaker. Oh, yes, okay, great. Thank you, Nicole. So if you have any more questions, you can hang on to them and there'll be a general discussion at the end. So our final speaker today will be Jiang Zhu. He's a project scientist at the Climate and Global Dynamics Laboratory at NCAR. And today he's going to be talking about cloud parameterizations and the last glacial maximum. So take it away, Jiang.
Hello, everyone. Thank you, Jana, for the introduction. I'm Jiang Zhu. So my presentation is about informing cloud parameterizations in CSM2 through simulation of the last glacial maximum. So last glacial maximum is one of the best studied past climates. And through the years, we have getting better and better understanding of it. So the latest estimation of the LGM is that the LGM is 6 degrees C colder than the pre-industrial. And the cooling, global cooling, is primarily caused by changes in the greenhouse gases and ice sheets. And it's thought to be provide the strongest constraints on the high ECS. So one straightforward way to use LGM to inform climate sensitivity is through performing paleoclimate simulations. The x-axis here is the LGM global cooling, here is ECS. The dots are different CSM versions. You see that we have a very nice correlation between the two. And the higher the ECS, the stronger the LGM global cooling in the model. So in the case of CSM2, we say that the ECS is higher than 5, and the simulated LGM global cooling is close to 12 degrees C, which is clearly outside the proxy suggested range. So the Tierney et al. Estimation here. That made us to conclude that the high ECS of CSM2 is very likely to be unrealistic. With the model, we can perform sensitivity experiments. That's the red here. So instead of using the latest atmosphere model in CSM2, that's CAM6, if we use CAM5, basically you see the results revert back to the CSM1 simulation. So this exercise is helpful. It tells us that the excessive LGM cooling and the high ECS is likely caused by the atmosphere model. That motivated us to carefully examine the details in the clouds between CAM5 and CAM6. So here I followed the approach in Gettleman 2019 in fully coupled CSM2 configuration to test the contribution from individual cloud schemes. So configuration CAM6 means everything standard, and head freeze off means you run fully coupled CSM2 with CAM6, but with the older version of the CAM5 as nucleation scheme. So similarly, MG2 off uses the older microphysics scheme. Club off uses the older CAM5 version of shallow convection and the PBL scheme. So this CAM5 configuration here means running CSM2 with CAM5 physics. For each of these configuration, I performed coupled LGM and pre-industrial simulation with major LGM climate forcing and the same initial computation. And in addition, I performed the slab ocean simulation for pre-industrial and 2 times CO2. The purpose of this simulation is to examine the state dependence in cloud feedback, which is thought to be challenging if you want to inform the cloud feedback and ECS using past climates. So let's look at the results. The figure here shows the LGM global cooling. So the data is black here. Colored lines are model simulation. So I have 100 years of fully coupled simulation. The figure on the right shows the shortwave cloud feedback in the LGM, fully coupled simulation, and the WCO2 slab ocean simulation based on pre-industrial. And you can see that CSM2 with CAM6 has a high shortwave cloud feedback. Therefore, we have this excessive LGM cooling. And the numbers are the projected LGM cooling. Because I only have a short simulation, here I do linear regression between the TOA radiation and surface temperature to estimate the projected cooling. And comparing to CAM6, you see that CAM5 running with CSM2 has a much weaker shortwave cloud feedback and a much reduced LGM global cooling falling within the proxy suggested range. Those are the sensitivity simulations to test individual cloud schemes. You see that if we use the old shallow convection and the PBL scheme, we have decrease in the shortwave cloud feedback. And with 100 years, we cannot tell the difference in surface cooling. But if you look at the projected cooling, so you can tell that still makes a difference, which is consistent with a decrease in the shortwave cloud feedback. The green and the orange are the simulation with the CAM5 version of microphysics and ice nucleation scheme. You see significant decrease in the shortwave cloud feedback, and you see much improved simulation of the LGM cooling. So this exercise tells us that there might be problems in the microphysics of the ice nucleation scheme, which guided our further exploration. So thanks to Andrew and the colleagues, we learned that there is a cloud ice number limiter that needs to be investigated. It is called NiMax. So this limiter sets the maximum cloud ice number, and it was designed to work with the old ice nucleation scheme, as well as the longer microphysical time step. And it was not modified when developing the new model. If you are interested, please check out this GitHub issue report and this manuscript in revision. So in light of that, we performed additional configuration. So we call it no NiMax. So everything standard CSM2 CAM6, but with this limiter removed. That gives us this yellow result. You see that compared to CSM2 CAM6, we have weaker shortwave cloud feedback. As a result, the simulated LGM cooling is also much reduced. So this is a very big improvement. And if you calculate the projected LGM cooling, again, using linear regression, so still, this is not ideal. There is another problem with the NoNimax configuration. The figure here shows the zonal mean in cloud ice number concentration in the CSM2 standard simulation and the simulation with in NoNimax. You see that without that limiter, the cloud ice number grows to values higher than 900. And this is over the upper troposphere in the mid-latitudes. So this is at least almost an order larger than the standard CSM2 and the observations. To improve this simulation, one obvious thing to do is to reduce the microphysical time step size. This is done by increasing the substep number. So here I increase the substep number all the way from 2 to 32. And you see that as the substep number increases, we see this reduction in the simulated cloud ice number. And after a substep number of 8 to 16, we see this converging in the solution. Then we added this fully coupled simulation with this NoNimax and 8 substeps in the MG2. So we have this black. So comparing to NoNimax, the yellow here, microphysical substepping further decreases the shortwave cloud feedback. As a result, you see that the simulated LGM cooling is more realistic. You can also tell that from the projected LGM cooling. And to make sure that 8 substeps is sufficient, I also have other simulations with different substep number, for example, 4 and 16 here. And you see that as the substep number increases, we see this decrease in the global mean shortwave cloud feedback, and a converging solution is reached after 8 substeps. So that's basically our configuration, paleo-calibrated configuration. So NoNimax and 8 substep in the microphysics. We added some minor tuning to improve the top of atmosphere energy imbalance in the pre-industrial simulation. Here are our final results in the LGM simulation. Paleo-calibrated configuration is in blue, and we have 500 years now. And it's still marginally too cold, but we think this is acceptable. This is certainly a major improvement over the standard CSM2 Chem6 simulation. With this new configuration, I performed a suite of DEC simulation. The left figure shows the abrupt 4 times CO2 simulation, a Gregory plot. You can see that the calculated ECS is around 4, so much lower than the value in standard CSM2. And if you do slab ocean to calculate the ECS, you get a similar number here. And I also quantified the aerosol cloud interaction. It's 20% weaker than the standard CSM2 Chem6. The red figure here shows the temperature anomaly in the historical simulations. The blue is the paleo-calibrated configuration. You see that it well reproduces the 20th century warming in the observations, that's the black here. And the performance is overall as good as the standard CSM2 historical simulations. So those 3 figures are Taylor diagrams summarizing the simulation of clouds. So those are from AMAP simulation with the satellite simulator enabled. I don't think I have time to go into details, but the key messages are from this one is cloud forcing. You see that we have small degradations in the shortwave cloud forcing and the long-wave cloud forcing. The middle panel shows that we have maybe a small improvement in the overall cloud cover. The right figure shows that we have improvements in the cloud phase. So you compare the blue against the red. So here is a summary. we developed this paleo-calibrated configuration with a 2-degree atmosphere. And we are very happy that we keep all the advanced physics package in Chem6. And the paleo-calibrated configuration has one fix to improve the physical consistency in the model, and another to improve the numerical performance of the model. So remove this NRMAX limiter increases the cloud ice number and mass, which indicates a more negative cloud phase and lifetime feedback. So without this limiter, the system can adjust to external forcings more freely. So substepping in microphysics also decreases the shortwave cloud feedback. So the paleo-calibrated configuration simulates realistic LGM, present-day observation, has a lower ECS of 4K, and we have weaker shortwave cloud feedback and aerosol cloud interaction. Hopefully, this is an example to show you that paleoclimate can be used to inform cloud parameterizations. I think the physical foundation here is the nice correspondence in the shortwave cloud feedback in the paleoclimate simulation and the present-day based climate simulations. So there will always be this small state dependence, but you say that it's always smaller than the intermodal differences. I will stop here. Thank you for your attention, and I'm happy to take questions.
Wow, thank you. That was a very nice talk. It seems like it's really structural uncertainties more than parametric, or you've made structural changes rather than just parametric changes to the model to calibrate it.
Can I ask a question, Christy?
Yeah.
So just to,
me?
I'm trying to paraphrase your talk in one sentence. Do you think what you've shown is that there was a problem in the cloud parameterizations in CESM2, and that's why the climate sensitivity is so high, and when you fix that problem, the climate sensitivity comes down to below 4 or about 4?
Oh, first, I want to acknowledge that I'm not an expert on the cloud microphysics, and the people can correct me if I say anything wrong. So I think there's physical reason to believe that this limiter shouldn't be there. So it produces inconsistent treatment about the cloud ice number and mass. So this limiter will artificially decrease the cloud ice number, but this limiter does not apply on the cloud ice mass. Therefore, this is clearly physically inconsistent.
Thank you. That's very, very interesting work.
Thank you.
Yeah. So again, if you have questions, type them in the chat or use the raise hand function. We have one question in the chat from Dan Lund. Do you think that additional calibration to other paleo time periods, in particular past warm periods, could further constrain model parameters?
Yeah, thank you, Dan, for the question. This is exactly what we are going to do next.
Cool. Andrea has a question. Maybe I missed this, but what is the mechanism that explains why increasing the microphysics substepping decreases the cloud feedback?
That part I don't have a good understanding. And if you check the zonal mean shortwave cloud feedback with different substeps, you'll see that maybe over the mid-latitude mixed phase cloud regime, so the substepping is making a difference over there. And I don't have a physical understanding about what is going on.
Cool. Well, okay, Eric has a question. CSM isn't the only model for which the latest version has a jump in ECS. Do you think your arguments apply more generally than CSM?
I think one important message I want to deliver is that please try your model in a paleoclimate configuration. and that's helpful. It tells us something. And about the details, I'm not clear because every model has different details in the cloud parameterizations. But still, I think this work and many of my previous works show that the importance of overall the cloud microphysical processes. I think at least it tells us maybe we need to be more careful regarding details of the cloud microphysics.
Nice. Ian has a long question. Ian, do you want to read it out loud yourself so I don't have to speak in your voice?
Sure, Christy, I'll be happy to try so it's so long, but I really enjoyed the talk. You guys can hear me, right?
Yes.
Yeah. I was curious how this matches with the results from this paper 15 years ago by Michel Crucifix in GRL called Does Last Glacial Maximum, the Last Glacial Maximum Constrain Climate Sensitivity? The thing I was struck by is that old paper, I think, asked the exact same question: can LGM simulations be used to inform ECS and cloud parameterizations? And it came to the exact opposite answer, which was no. And I'm just trying to get my head around how these two approaches differ. So I think this figure that's on the screen right now is kind of the crux for me of this one, was that ECS and LGM global cooling correlate really well among versions of the NCAR model. Crucifix, I think, looked at more or less the same thing, but it was among different GCMs participating in PMIP. And he found there was no correlation. And he found the reason was the cloud shortwave feedback being nonlinear, so cloud shortwave feedback was sort of central in both stories, but played an opposite role. And so I'm just wondering, given what these other models did in that study from 15 years ago, should we be worried that what you're looking at is some idiosyncrasy of some aspect of the NCAR model?
Yeah, thank you, Ian. That's an excellent question. I think it's complicated in other aspects of the feedback because the forcing differs in different models. For example, if you check the forcing from the ice sheets, if you only look at the shortwave component, you'll see that maybe the values range from 2 watts to maybe almost to 6, I guess. So the forcing itself ranges has a large range there. And maybe people treat the albedo of glaciers differently. There might be other reasons. And another thing is, that's the forcing part. And on the feedback part, cloud feedback, of course, differ by in different models. And there's other aspects, for example, the ice albedo feedback. So in order to get a realistic LGM simulation in terms of the temperature and also deep ocean, you need to reproduce the sea ice expansion over the Southern Ocean, which means a very strong positive feedback is there. So I guess it's not captured by all the PMIP models. And to simulate the Southern Ocean processes, you not just need to simulate the sea ice, it's fully coupled with the Southern Ocean dynamics. So it's maybe not easy to do. And the PMIP models, I guess, don't show a consistent picture there. Hope that answers your question.
Yeah, I wonder if a paleo AMIP simulation would help here. Okay, Isaac has a question. Where is it? It seems that model versions either have LGM cooling of about 6 or larger than 10. Is there a bifurcation? Is CSM2 LGM close to snowball Earth?
Yeah, that's a good question. So in the whole process, I did tens of decades of CSM2 LGM simulation. And there indeed was simulations maybe going towards the snowball Earth. And it's not surprising that we have a strong amplification effect from the sea ice albedo. But regarding the bifurcation, I think to be clear about that question, we need further exploration.
Torsten, as a follow-up, along the lines of Isaac's question, I was curious if the model has actually been run to equilibrium. In one slide, it says minus 12 K cooling, but in another, you seem to extrapolate and get minus 19.
Yeah, this one is 1 degree. And for the other results, they are 2 degree. The 2 degree model is more sensitive than the 1 degree. Yeah, with 100 years, a lot of the simulations are not in equilibrium, but we can still calculate the cloud feedback, and the difference in the cloud feedback contains important information there.
Nice. Okay, there seems to be some more discussion in the chat, but neither of them seems to be a direct question. So we can use the last 10 minutes for a general Q&A. So if you've thought of more questions or discussion points for Nicole's talk as well, feel free to again put them in the chat or raise your hand. Okay. While people maybe think of questions and type them in, I guess I have more of a philosophical question for Jiang. Given you seem to have, again, maybe structurally tuned CSM2 rather than fitted individual parameters. So does this mean that if we're trying to do the same for other models, calibrate them to say paleo states, this has to be done again ad hoc? Or do you think there's a sort of more general way to calibrate these GCMs to other states?
Yeah, I think that's a good question. I think for us, we have multiple lines of evidence on the table. And if we move forward, we need to check each lines of evidence. And we want to include paleo in the whole process.
Cool. Okay, Nader has a question. Nicole, I'm curious, how do you think your results/conclusions might change with the use of relative humidity feedbacks a la Held and Shell 2012? The lapse rate feedback seems to be much weaker in the relative humidity framework.
I think that's an excellent idea. That was definitely on my mind when I combined the water vapor and lapse rate feedbacks and saw that then they kind of collapsed onto this one-to-one line when you're thinking about Arctic amplification. And so I haven't done this yet, but my thought is that if you use the relative humidity feedback instead, you would, again, just like in the global feedback framework, you're reducing a lot of that spread there. You would see the same thing thinking about polar amplification. And then if there were, if you did then have that relative, you might expect that relative humidity feedback to kind of contribute to Arctic amplification in that framework and make things a little bit more clear about how the water vapor and lapse rate feedbacks are compensating. So I think it's a great idea. I think it might really help.
Thanks.
And also that relates back to Jonah's question about the state dependency. I think that if you're, I think that could help kind of clarify if you're in the ice regime and then you're seeing having a positive feedback in that case, when you no longer, that would possibly show up also in the relative humidity framework. So I didn't explain that very well, but.
Thanks.
Nice. Well, if if there aren't any more questions, and given that we've only had 2 speakers, I think we can end a few minutes early. I want to thank our speakers, and thanks everybody for the questions and the engaging conversation. And we'll see you next time. Again, if you want to give a talk, let us know.